So good afternoon or good morning, everyone, and thank you very much for joining us to this GEO at EFR seminar. Today we have the pleasure to welcome Guillaume Duclaux from the University of Côte d'Azur, and he's going to tell us a lot about numerical modeling of continental rifting. And I think all of us, wherever we are welcome you very warmly, Guillaume, and I'll leave you the floor.
Thank you very much, Catherine. And thank you very much for the invitation. It's a pleasure to be involved in this sort of seminar series. So I'll try to present you, like in the next 45 minutes, some of the work I've been doing on numerical modeling of continental rifting. This is not only my work. Before I start, I'd like to acknowledge all these people here at the bottom who I've been working with on developing codes and using codes or interpreting data. This is definitely not a single person effort, so I don't want to have all the acknowledgements for that. So yeah. And on this note, so I'm going to discuss three different aspects of rifting. First of all, how rifts sort of propagate in 3 dimensions on Earth. We're going after to dive more into oblique rift architecture. So we're going to discuss some of the results of our model and compare that to natural example to see some of the structural evidence of the progressive deformation and formation of oblique rift system. And I will very briefly at the end of my presentation go more into the surface processes aspect of tectonic in continental rift system. So let's start. Yeah, so when you think about rifting in general, we think about either continental rifting or passive margin, eventually some spreading center in the middle of the ocean. And what we have in this region is mainly extensional features, right? We've got extensional fault, normal faults, detachment, which are present in this system. And you've got here tectonic map, tectonic activity map of the Earth, where you see the plate boundary, which are marked here in red. You've got the divergent plate margin, in blue the convergent plate margin, and in black you've got the transform plate margin, which are there. And generally rift system, so some of the most famous one, they're associated with normal fault, with spreading, and with extension. So the rifts, they do form during continental breakup or supercontinental breakup, and some other people before, like if you listen to Giacomo presentation, for example, he mentioned the importance of inherited structure for controlling the formation of rifts. So it's a bit of a chicken and egg sort of dilemma. Did the rift come first, or did the orogeny come first, and what influenced what? So I'm not going to go into this, but we're going to look together a bit more at a continental rift system, which is the East African rift first. And here, so if we define what is a rift, from a tectonic point of view, here on the picture on the right, you've got a photo from David Pyle, which is an aerial view of the Dabau Manda Araro rift in Ethiopia. As far as I can tell, it's in Afar. And you see these volcanic plateaus, which are cut through by normal faults, and this normal fault creates this nice depression here in the middle. There's a stratovolcano at the back, so it also means that there is some volcanic activity today in this system, in this rift system, and we can see the East African rift here, which is going from the Afar depression here, where you've got the 2 branches here of the Gulf of Aden and the Red Sea, and you've got the main Ethiopian rift, which is cut into different bits and pieces. I believe there are 3, the north one, the central one, and the southern one. And after, the rift separates into multiple branches further south, avoiding a big crater. So if we look at the geodetic data for this rift system, and you've got some maps here with GPS data and some kinematic models that was proposed by Stamps and co-authors in 2014, we see that the rift sort of main direction is slightly oblique to the plate boundary, right? And that's it for me. If we go a bit further into the evolution of continental rift, after you can they tend to evolve eventually into passive margin or oceanic yeah, passive margin and basins. So you've got two reefs that are well studied here on this Google Earth sort of view of the Earth. You've got the North Sea here, which is a continental rift system where you've got a lot of opening, a lot of stretchings that happened between Scandinavia here and the UK on the other side, and on this side here you can see the passive margin on the side of the North Atlantic. And people have been studying this system using seismic imaging and trying to retro-deform this kind of system to try to understand how they form. So this is a sort of 3D sketch view designed by Akon Fossen and some co-authors of the North Sea, where you've got the central Viking Graben and different platforms which are present here at different depths. Excuse me. And if we look like in the North Atlantic region, you've got two passive margin with extended domain where you've got normal faults and very thin continental crust, which stretch after towards the oceanic domain where you've got true oceanic lithosphere that formed in along the spreading ridge there. In these systems, in general, when we look at the deformation in map view here of the whole Earth put on a map, you can see the stress which have been measured in different places, and the color of the small symbols here, they depend on the orientation of which of the principal stress axes is vertical. In red, you will have the domain which are under extension, dominated by normal faulting, where the maximum sort of principal stress direction is vertical. So sigma 1 is vertical, so that's going to be in red. Places that have the minimum stress eigenvector vertical are in blue, so there's a thrusting region, convergent domain. And in green, you've got places with the intermediate stress direction, which is vertical, that correspond to the strike slip. And what we can see is that the world is very sort of, well, there is a lot of red. There is a lot of extension going on, both in rift system along the East African rift, for example. Also along spreading centers here, you see a lot of red dots, but also in origin. And if I zoom in a little bit, here you've got a view of Africa and Europe with the Arabian plate here. And you see a lot of these markers are actually indicating that normal faults seems to be dominating not only in rift system, but also in origin. So normal faulting is very important in understanding the evolution of plate dynamics and today tectonics, right? And this has been studied for now more than 30 years, almost 40 years, by tectonicists using modeling technique. And I'm going to start with that, starting first with some insight into analog modeling. And these analog models have been really key to unraveling the 3D dynamic of rift system. Some of the first models from Maclay were kind of 2D sandbox experiments where they stretched the model and they added some sediment as it go. And you can see some very nice structure in a major fault here, and you see some structure in a sediment that show the deposition which is going to accommodate the extension in the system. There's some work from Brun here which are a bit more sort of lithospheric scale, where they use this plasticine experiment where they've got this bunch of silly putty or silicon putty and sand layers that they stretch, and they look at the formation of rifting. You see some necking zone, you see some beautiful structures that people recognize today. And if you move a bit closer in time, in the year 2010 and around that, and after that, you've got some amazing 3D sort of models that came through with people studying orthogonal rifting and oblique rifting. For example, you've got some model from Agostino or Corti in the year 2009 and so on. And Frank, who I see here is connected, who did also a lot of analog modeling of orthogonal rifting, but also oblique rifting and reef propagation. So some of the advantage of this analog model is that they've got a fantastic resolution, both in 2D and 3D. You see beautiful structure at the surface. It's pretty amazing what you can do with the sandbox, I suppose. And some of them can be scaled. Also, there are still some issues with that. Scaling is not always easy to do, especially with gravity. So people have been using this centrifuge system to try to scale a bit the gravity with the dimension of the model. And generally, it's difficult to, or it used to be difficult, it's probably better now, to stop the model, look at it, do some internal analysis of the structure. You pretty much have to run your model for the whole time. And then after you freeze it and you cut it and you do some imagery and so on. So these were some of the limitations of rifting, of analog models of rifting. And then numerical models sort of evolved or improved, and people have been looking at modeling this type of structure using different type of methodology. The nice thing with numerical model is they can be scaled easily, they're easily reproducible, and you can access some very fine physical property and their evolution. So in analog model, you have to generally set the rheology by blocks. So you tend to have a kind of unique behavior for different layers. Here in numerical model, which can be this kind of discrete particle element here, some work from Hardy, or a finite element model, some work here from Hausmann and Beaumont, or Nalibov and Britta, really allowed to look at complex rheologies and testing different kind of rates for the evolution of rift, and looking how weakening also affected that, and you could have multiple rifting, so on, with rift migration and reactivation. So it opens really new ways. It was done at very high resolution, mostly in 2 dimensions until the year 2010-ish. And it allowed to define, I mean, some of these papers from Buck are very famous for people looking at rift system, where he kind of defines the 3 modes of rifting, where you've got this narrow, wide, or core complex system, depending on the rheology of the system and how quickly you pull on new plates. And they're really good, but generally they were 2 dimensions. And what I want to show you today is how we push that a little bit into the 3rd dimension, because 3 dimension is really key when you work on a spherical planet and when you look at how structure tend to propagate in space. So the objective of my talk, as I told you in the first slide, I'm going to try to convince you that numerical models are useful to unravel the dynamic evolution of rift system. I'm first going to spend about like 10 to 15 minutes looking at the rift propagation system and try to estimate the forces that drive this rift propagation in 3 dimensions. We are going to try to measure the relative contribution of tectonic and body forces into this system, and going into the famous passive rifting versus active rifting. So this will be the first part. Then I'm going to go into the more oblique rifting sequence, which is well aligned with the previous presentation from Giacomo, where he gave a fair bit of information about the East African rift, or the main Ethiopian rift system, where he compared some of the distribution and orientation of fault in the brittle crust, and I will go through that and explain to you what we see in our numerical experiments. And finally, I will take like 5 to 10 minutes to show you some of the most recent works that we've been doing to try to assess the links between normal fault geometry, surface uplift in rift system, and how it's going to control the fate of sediment in active rift. And this is specifically looking at the current rift in Greece. So how does a rift propagate? Well, Earth is kind of a sphere, and when you've got 2 plates which separate from each other, generally they rotate, they spread from an Euler pole, where you've got your rotation axis. And depending where you are, if you're really close to the Euler pole, you're going to have very strong gradient in velocity opening, and if you're further away, you're going to have much faster velocities. These kind of features are very obvious when you look on Earth at rift system. We can look, for example, on the Central Atlantic province here, or the South Central Atlantic province, where reconstruction shows that Africa here and South America on the other side, when they separated at around 130 million years ago, they didn't separate like that, but it was a kind of V-shape, scissor shape opening. and you had a reef propagation from the south towards the north, right? We've got evidence of that also in the Gakei Ridge at the top of the Earth. This is Greenland. You've got Svalbard here. This is Russia. And on the north here, you've got beautiful propagation of a V-shaped system, and you can see the velocities, the spreading rate of the oceanic ridge. They decrease toward this point here, where you've got eventually compression when you're here on Earth. So the Euler pole, the rotation, the pole of rotation will be somewhere here inland in this area, and the spreading is tend to propagate in this system. There are some beautiful examples here also in the East African Rift, where you've got some spreading going on. You've got that for the Red Sea here, where you've got active sort of spreading of the rift. Oops, sorry, towards the north in this system. So this is what we want to model in our numerical model. And to do this modeling, I've been using a code which is open source and open access called Underworld, and it's a code that Catherine knows quite well, as far as I can tell. Developed by Louis Moresi and collaborators. It's a 2 or 3D thermomechanical open source tool that is designed to solve heat transport and incompressible viscous plastic Stokes problem. So you have some conservation of mass and momentum in the system. You define some rheology, either viscous or plastic, and some sort of thermal equilibration for the material. And you're going to solve for the pressure and velocity on a set of elements that you define in a system. In this model, the material properties and their history is actually stored on small particles, which are going to flow inside a mesh. And after every step of calculation, we are going to recreate a regular mesh, and the particles are going to preserve their whole history in there. And it's using it's called a particle in cell finite element formulation. It's using a multi-grid sort of strategy for solving this type of Stokes problem. So the model that I'm going to present you is this one. You've got a 500 kilometer by 1,000 kilometer model. And we actually did 2 models next to each other. One, which is the classical sort of orthogonal rifting, where the velocity along the side of the model is set to be constant all the way along the model at 1.25 centimeter per year on each side. So we open at 2.5 centimeter per year. And a second model, which is rotational, where the velocity on the fast side is going to be 1,000 times the velocity on the slow side, right? This will be equivalent to say that in the rotational model, we've got the Euler pole outside of the model here at about 100 kilometers of the model, and we are going to compute the way the structure, sort of the rift or the extension is accommodated into this system. The model is a relatively simplistic layered cake. You've got air at the surface to allow for surface deformation. There is an upper crust which has a viscoplastic rheology, which is defined as a wet quartzite, and a lower crust defined as a mafic granulite. The crystal thickness is about 40 kilometers. The temperature at the MOHO is at about 520 degrees. And then the mantle underneath is composed of a wet olivine rheology. We impose a small notch which cross over the model here to localize the deformation in the center part of the model to avoid any sort of boundary effect in here. And what I forgot to mention is at the base of the model, the material is going to inflow inside the model to balance the pressure pretty much along on a column. And yeah, so this is a paper by Luc Mondy and some co-authors, including myself, that was published in 2017 in Geology. And you've got a view here of the model, and I think if I do that, you should have a nice animation. So the fast side of the model is here on the south, and the slow side is here on the north. What you see at the surface is a color scale for the elevation. When you've got this brown whitish color, it means it's quite high. When you go into the green and blue, it means it's deep, right? On the side here of the model, you see in red the strain rate second invariant. So this will be the active localization on shear zone and fault. And the white and black code that you see with the horizontal stripe for the upper crust and vertical stripe are just markers to see the deformation inside the model. We show the temperature here in the mantle, and the 1330 isotherm marking the transition between the lithosphere and asthenosphere correspond to this kind of red stuff which is rising there. So what we see is that through time, we tend to localize deformation faster in the south, and it tends to propagate further north. I'm just going to go to the next slide to show you what is going on at the surface of this model. So these are views of the two models. The orthogonal model is presented on the left here, and the rotational model is presented to the right. For the rotational model, the fast end is here on the right side, and the slow end is here on the left side. We've got snapshots which are at different times. So this first time shot is at 0.5 million years. The second one is at 1.5. We go to 3.6 and about 6 million years. The color scale that we see at the surface, so it's either red, blue, or green. It's a similar color scale that I show you on the world stress map, pretty much. When it's in red, it means that the principal stress eigenvector is close to vertical. So sigma 1 is vertical. It means you're going to, oh, sorry, when it's blue, it means that you've got extension dominating in the system. When it's red, it means that you've got compression dominating in the system. And when it's green, you've got transcurrent tectonics going on. The darker the hue of the color, the more high strain rate you're going to have. So what we see is we identify different phases of deformation in our model. And the first phase of deformation is a distributed deformation. So we see here, so it happens before 0.5 million years in the orthogonal model, so we don't see it. But we see that along the rotational model, we've got this domain here with very limited strain localization. We've got quite distributed deformation all across the model. And then after, you've got a phase of strain localization with an axial graben that forms. And on the side, you've got sort of normal folds that are going to sort of create a depression in the center. And this depression is kind of stuck between two normal folds. So the deformation that is going to happen in this sort of flat graben is going to be compressional in a sense, right? Because you pull there and you're going to squeeze between two normal folds your system. As deformation progresses in our model, we see that we've got a phase where we've got localization on progressive localization on the internal part of the graben here, which used to be in compression. And we see through time that there seems to be a migration of the deformation from the fast side of the rotational reef towards the slow side. And we've got a phase 2 deformation going on here next to the Euler pole, and phase three here is dominated. You've got a wider rift system here. And then the phase 4 is a breakup, and you see breakup initiation, which is quite obvious in this model. The breakup occurred in this model at 3.6 million years. You see that the breakup occurred up to about half of the model dimension. In the orthogonal model, breakup occurred already, and you see most of the strain localization is actually along this now spreading ridge system. And as the model go, we've got some real oceanic spreading and localization really limited on a very narrow band here. And we see some also inversion of the tectonic activity with compression on the passive margin, which seems to propagate. The last snapshot that you see here at the bottom, there's the sort of ill-shade topography of the model. So the darker the color, the deeper it is. And what you see here is that you've got a sort of deep oceanic domain, and at the front of the propagating sort of reef tip, you seem to have a deep basin, which is present in this system. And what we wanted to understand is what are the drivers for this rift propagation? And the way we look at that is try to compare the gravitational energy that is present in the rift when you take a column here around the center of the rift and one in a domain which hasn't deformed. So I just moved one slide and I come back to the previous one. To do this measurement, we use the gradient of gravitational potential energy, delta GPE. So it works very simply. You take a column here, or you take multiple columns here, and you assume that you've got a compensation depth here at which the pressure of this column must be equal. This is what the isostasy is saying if you take a classical model. And we're going to compute the difference in sigma ZZ, we integrate sigma ZZ, along each of these columns, and we compute the difference between the column C here and the column B and the column A. And what you see is a gradient, how the gradient of gravitational energy between these different columns is presented. And the region which have a high GPE will tend to exert a net force towards the places which have a low gravitational energy. So you're going to, here in this system in 2 dimensions, where you've got your asthenosphere, which is rising to the surface, it is relatively low density compared to the lithospheric mantle here. It's going to push the system toward B here. So when we look at that in the model, we did some section in our orthogonal experiment, and that you see that at the beginning, when the asthenosphere is rising here, the arrow here is showing a 5 centimeter per year velocity. You've got extension dominated in the system at 3.6 million years. At 5.9 million years in our system, we see that in the mantle lithosphere, the deformation is dominated by horizontal compression. It means that the asthenosphere rising here is actually pushing the material away. This is a transition between the classical sort of passive rifting, where you pull on the system and the asthenosphere rise passively, and active rifting, where now the mantle, the asthenospheric mantle rising, is able sort of to create its own space and push the material away. This was evidenced already by Hausmann et al. in 2001 for 2D Reef model. And what we wanted to check was how does it work in 3 dimensions, not across the rift, but along the rift propagation. And this is what we did in this model. And in this model, so you've got 2 sections of the rift sort of experiment. You've got the map view here, the section B here, which is orthogonal to the rift in this direction, and the section C, which is from the slow end towards the fast end. And the beauty with numerical models compared to analog models or nature is you can stop stuff. So we did play, we did let the tectonic go in the system for about 4 million years, up to 3.6 actually. So we pull on the system with using the gradients that I introduced to you before. And then at 3.6 million years, we stop the model, remove the tectonic forces at the side, and look at how sort of internal forces were sort of, what was I doing pretty much in this system. And what we see here, this is a model with which is called here the gravity-only model, 3.6 million years. You see that the asthenosphere rose here, and is actually, when we stop pulling on the model, we can still see some dynamics in the asthenosphere, and it seems to demonstrate that the asthenosphere rising is pushing the model apart. So we've got here in this model a stage where we already transitioned from passive rifting to active rifting. But what was most interesting and new in this model was the fact that we demonstrated that it also happened like along strike the rift, where we see here when we stopped the tectonic forces, we can still see that the asthenosphere wants to rise towards the slow part of the model. And there is a gradient of gravitational potential energy if you compare this column here with this column there. So you see the value calculated by the sum of sigma ZZ, we've got 3.8 10 to the 14 Newton per meter, is larger than the integrated gravitational potential energy that we've got here, which is 3.7. So naturally, the system is going to want to propagate towards the slow end because the asthenosphere rises high enough. This is just a picture of this gravitational potential energy maps that you've got here. And the triangle here, so it's only half of the model, and you see its evolution through time. And what we see is a breakup propagation. When the continental crust completely sort of break apart, and you see that the breakup propagates slower and slower in time because we pull at very slow rate in this part of the model. And we see that we've got a high gravitational potential energy here and lower gravitational potential energy towards this end. So we create gradients in both across strike and along strike the rift. And we're able to sort of estimate the driver of this propagation. And you've got a picture here of the lab, the lithosphere asthenosphere boundary, and how it sort of rises into the model and propagates through time. Then we compared our model and we went back into nature, trying to look at natural example of V-shaped propagator like that. And we took two examples that seem to work quite nicely, where you've got this, here this is a woodlark basin just east of Papua New Guinea, where you've got a small oceanic basin here, the woodlark basin with a rift which is propagating toward Papua New Guinea. And what is quite nice and interesting compared to our simulation here is the fact that you've got quite a diversity of earthquake focal mechanism, where you've got some compression going on the side of the model, which might be comparable to what we see in our model, where we see phases of inversion along the margin of the rift. And you see that when it's going towards the propagating tip here, you've got this very deep basin, which is just east of PNG. This is something that the model predicted in a sense. It's actually that when the asthenosphere flows towards the slow hand, towards the propagation, it kind of sucks material before it propagates. And we see that also in a more oceanic setting. This is in the middle of in the Pacific, where you've got the Coco Plate, the Nazca Plate. Here, that's the Galapagos microplate you've got here, and the Pacific Plate here. And there's a super deep depression here, which is called the Hess Deep, which is a region which is, and you see the V-shaped propagator where it seems to open kind of obliquely like that. If I do it with my hand, it's going to be like this, right? And right at the tip of this kind of V-shaped structure that you see in an oceanic system, you've got this low thing. So we believe that this is a good argument to say that asthenosphere flow drives rift propagation toward its solar pole and generates this transient over-deepened basin as it progresses. We also looked at another example a bit closer to where I am at the moment in France, the Bay of Biscay, Gulf de Gascogne in French. And it's just north of the Pyrenees. So you've got Spain here, France here. And so the Pyrenees now is a compressional origin. So this stuff has closed, but at some stage, this sort of V-shaped Bay of Biscay open. And you've got super deep basin, which are right at the tip of this V-shaped system, which is one basin is called the Parentis Basin, which is quite famous. And you've got some seismic section here of Tugend and co-workers, which they interpreted here. And you see the basin is going, this is in two-way time, so it's not migrated. Oh yeah, it's migrated here. The basin is going as deep as about 20 kilometers and filled with sediment in this region. And what is very interesting, and maybe this is pure luck or whatever, on this section here, you see some inverted structure which are documented with thrust system on the passive margin. We're quite far away from the Pyrenees. There's no good reason for this structure to be related to the compression of the Pyrenees. And we believe this could be sort of a witness of these phases of compression that goes during your propagation of your rift through time. So the model works quite nicely, or at least we believe it works quite nicely. It allows us to propose some sort of processes for the evolution of this rift system. But we've got a problem. We still try to model the Earth in a shoebox, right? So we've got a shoebox, and it's going to create weird stuff if you kind of project your grid onto a sphere after. So we actually create some compression in some domains around the system and so on. So this was not really optimal. And the way to go will be able to do some modeling of the whole Earth without any boundary condition. I haven't done that, but some colleagues did. This is some famous work published in 2019 by Nicolas Coltis and co-workers. I don't know if you put, there is some music which is playing in the back. What you see is a sort of all spherical Earth model, and the white domain here, they show continental masses. And what you see in red are the kind of hot material rising, and you see the formation of spreading center and propagation of rift. It's quite fast. This model was tried to reproduce the whole sort of framework of plate tectonic sort of motion and velocities along with the mantle tectonic. So it's, I believe it's quite impressive, and that's the way we want to go in the future, I suppose. Okay, I'm done with the rift propagation, and I'm going to dive into my second part, which is about oblique rifting. I'm not going to convince you. I think you can look at the presentation from Giacomo last month, that oblique rifting is the rule pretty much. And Sacha Brun and co-workers did publish a fantastic paper where they reviewed the obliquity of the structure on passive margins and active rift system. And really, because we're on a sphere, when we have got stuff moving at different velocities, obliquity is really the way things deform, right? Orthogonal rifting, where everything happens in 2D, is not really easy to do on Earth. So about 73% of extensional margins strike at less than 60 degrees of the plate motion direction, right? So we've got an obliquity of more than 30 degrees for about 75% of all the plate margins on Earth. So oblique rifting is important. Rift tend to localize based on tectonic inheritance. If we look at the North Atlantic, for example, you've got the Variscan origins. Oh, sorry, not the Variscan, but damn it, forgot. It's not coming back anyway. Older origin system that was running through Scandinavia and Greenland, and the North Atlantic rift seems to sort of form right there and propagate and cut through this old origin. Another important feature for rift propagation, I think, and that wasn't discussed a lot as far as I remember from the presentation from Giacomo, is the importance of hotspots. In East Africa, for example, you've got the East African rift. The IAIFR depression is actually where it is. It's sitting on top of the IAIFR hotspot. And the fact that volcanism is decreasing when you go from south to north is also probably related to the fact that you're close to the hotspot when you're toward the north, and you go further away when you go towards the south. So these two things altogether, local heterogeneities, which can also be cratons here in the south, where you've got craton roots which are deeper, and tectonic inheritance are going to have a strong importance on controlling like rift structure. And if I go a bit closer to the sort of north and central main Ethiopian rift here, these are some maps from Corti et al. It's a system where that trends at about 60 degrees from the plate motion direction. And if you look in detail, as Giacomo presented that quite nicely, the northern part and the central part even have a different sort of obliquity compared to the velocity of the actual sort of plate motion direction that we see. But overall, if I oversimplify this system and don't look for any kind of volcanic activity, we've got two generations of normal faults, right? There's the border faults, which are shown in black in here, which tend to be oblique faults, and they seem to be controlled by pre-existing structure, or they tend to link at least maybe the IAIFR hotspot and some depression further south. The second set of faults, which are quaternary and active today, are the ones which are inside the East African rift, and there's the Wanji faults, and they're mostly normal with an extension direction, which is almost in pure deep sleep displacement compared to today's extension direction. So these are the observables that we've got in a sort of young continental rift. If we look in a more sort of evolved system, we take the Gulf of Aden, for example. And it's another very nice example of oblique rifting, where the trend of the basin here is oriented at about 50 degrees or 45 degrees from the plate motion direction. You've got a structural style that varies along the Gulf of Aden, probably because of, if you go far away from the IIFR depression here, you will have less influence of the IIFR hotspot. But what is quite striking is the shape of the margin, where you've got this kind of zigzag shape structure, where you've got asymmetric sort of large margin on one side and narrow margin on the other, wide, narrow, and so on between. So sorry, I forgot to say, the line in blue here is a continent ocean transition line. So your passive margin are very dissymmetric, and the Gulf of Aden is a bit complicated because you did reactivate some Mesozoic graben which were optimally oriented orthogonal to the extension direction. But again, there are some different type of structures. Some are oblique, some tend to be orthogonal, and we wanted to test that in our numerical models. So we're not the first one to tackle this problem, of course. The analog modelers, they started to look at that first, because they can do fancy stuff in their sandbox. And what came out of these studies, and you've got a bunch of references, and the first one was really the work of Widjack and Jamison, but it goes further in time, is that the main extension direction, or the extension direction, is to have an intermediate angle between the rift and the plate divergence. So if you've got an obliquity of 30 degrees here, you're going to have a main extension direction at about 15 degrees. So you expect structures that form inside your weak domain to have an intermediate oblique direction when they form. This is what they see in a sandbox experiment and in also very simple stuff. And 3D numerical modelers try to follow, of course, with the 2D numerical models I showed you in a very early part of the introduction. You cannot look at 3D problem like oblique lifting. You need 3D to be able to do that. And the very first model, so it should be a one, was some work from Van Dijk in 1995. She was the first to try to model this kind of oblique rift system. And then after, there's some work from Alken et al. And a lot of work from Brun and Brun and co-workers in the year 2012 and 2014. And they did evidence that you've got this very nice kind of pattern of depression that formed inside this system, and you've got high strain rate on structure which tend to be oblique. But the thing with these models, they tend to have quite coarse resolution, and it was not that easy at that time to try to look really at detailed structural pattern evolution. So this is the model setup we used. We used another code called Pétatin, which is based on PETSI, so something very much like Underworld, the first code I showed you. It's a ridiculously parallel software that run on HPC. And we designed the model. It's a very simple model with a sort of 3 layers on top of each other. You've got a crust, which is made of wet quartzite, a wet olivine mantle, and another part of the sublithospheric mantle underneath, still made of olivine. We define inside this model a weak zone that we're going to rotate to impose some obliquity in our model, and we pull, or actually we allow the material to escape the model here on the side along the X direction. The surface is free to evolve. So compared to the previous model I showed you, where we had to impose some air at the surface to allow for the surface to move, here it's a true free surface here. The front side and the back side of the model, they're free slip, so they're pretty much 2D models on the side. And we impose viscoplastic rheology in the model. The temperature at the MO is at about 550 degrees. The way it works, the weakening, I'm going to talk to that just in this slide. We start the model with this weak zone, which is 300 kilometers wide, and we put some random noise into it. We assume that this is an inherited structure, probably something like an old orogen, where you've got some pre-existing fabrics which are there, or the rocks are already weakened, and they're weakened both in the crust and the upper mantle lithosphere. And we played with the orientation of the structure. And the way we set weakening in this system is we tell the code that when a particle is going to accumulate plastic strain. And when the amount of plastic strain increase above 10%, between 10 and 50%, the cohesion and friction angle are going to decrease. The friction angle is going to decrease between 15 degrees to 2 degrees, and the cohesion of the upper crystal rock are going to decrease from 20 megapascal to 4 megapascals in this model. So we play on these two parameters. So this, as I told you, it's run on Pétatin, which is another open source code. You can download it, play with it. It's available. It's developed by Dave May, mostly, and some other people. And it's designed, again, to solve this heat transport and incompressible viscoplastic stokes, and it has this deformable free surface. These models are very large, very high resolution. They're like horizontally 2 kilometers by 2 kilometers and 1 kilometer vertically for a domain which is 1,200 kilometers by 1,200 by, I can't remember what it was, 250 vertically. And it means that we have to solve for pressure and velocity and temperature, so about 1 billion of unknown in this code. So this was run on a supercomputer in Norway, in Trondheim, called Vilje, on 4,000 cores, and it did compute in 150 hours. We did manage to model 23 million years of natural evolution. So if you had a single core computer, that will mean it's 70 years of calculation, pretty much altogether. So there's real advantage of using supercomputer. And one simulation generates about 10 gigabytes of output. So it's very large. It's a bit of a nightmare to deal with. So this is what the model looks like. You've got a map view of the model, and the color scale is the strain rate, so the active deformation in the system. You've got the time, which is shown here at the top, and what we see, so this hill shade, you've got the light is coming from this direction. So here it means that you will have a slope looking towards the east on the side here. I'm just going to play that again. So we start the model here. At the beginning, there's no deformation. You've got distributed deformation, and then after you create this nice graben that tends to widen, and then they kind of disappear and they preserve on the margin, and you've got much smaller structure which form inside the model and tend to interlink up to the time where you've got here breakup and propagation of the oceanic ridge from the two sides of the model. So the obliquity of the model was set to 45 degrees in this case. And I did develop a workflow to automatically measure the direction of the fault from the system. So I used what it's called, Python to do some image processing technique. So I started with my surface map and looking at the strain rate segment invariant, so the active deformation pretty much. It allows me to create this sort of white and black image, a segmented image, where I take only the domains which have a strain rate higher than a certain threshold that we define to be 10⁻⁻15 per second. And from that, I used some mathematical technique to extract what is called a skeleton from there. And on each of these faults, which is a straight segment, I can measure the orientation and the length. And I can take that automatically and compute the distribution of the structure along this model. And I only did that for the central domain to avoid any problem with the edge of my model, which are free slip, so they tend to force a little bit the system, right? And so I create this nice sort of Ross diagram with a fault which are scaled based on the length of the fault and the orientation. And I can also, because it's a numerical model, compute which of the horizontal sort of stressed eigenvector, so sigma 2, that will be the direction of propagation of the fault according to an Andersonian theory, if you want. And what you see here is a model where, I don't remember, it's a video, okay. So it's, just let the movie play. You've got two models. This one has a 30-degree obliquity, relatively low obliquity here. This one has a 45-degree obliquity. We start with this distribute localized deformation. I let it play and I'll come back to it in a second. So if I do that, yeah, we start with diffuse deformation, then it starts to localize. It localizes from the edge. And as it goes, we create this segment, which are about 110 kilometers wide. They're en echelon, and they tend to rotate toward orthogonality to the extension direction. Then we've got a second phase where we abandon this early structure and create new structure, which seems to be oblique, the second generation of shear. They're much shorter. And at some stage after, you've got breakup, which is propagating from the side of the model towards the central part, and you preserve these two generations of structure on the margins of the model. And as I showed you before for the reef propagation, I can look at any time in the model at the type of deformation regime at the surface. Again, in blue, you've got the places in extension. In green, you've got the places which are in transcurrent deformation, and in red, places which are in compression. That's the surface view. And what you see is that it's mostly sort of pure extension going on here at this model. This is the moderate obliquity model at 8 million years. And the sort of contour in black is showing the strain rate region, which are larger than 10 to the minus 15. So because they're 3D models, we can also look at these 3D models in 3D. So I took a section inside this model. You've got the isotherm here. That will be the 1330 isotherm, the one at the bottom oops, sorry, I'll come back to that, in white. That will be the 600 and that's 330. You see the shape of the topography, and what we see here is a finite deformation of the model. So we can see the localization pattern at the end or after 15 million years in our simulation using some passive sort of markers that I put in my model. The surface in gray, which is slightly transparent here, is a lithosphere-asthenosphere boundary. And you see that it creates some bulge, and this system interconnects and accommodates the deformation. You've got structure which are preserved on the margin here, which is your first sort of set of grabens that form en echelon. And after you've got the activation of system in the central part of the rift here. We can calculate also from the model this thinning factor for the crust beta and for the lithosphere. And you see the result here. This is the thinning factor for the crust and for the mantle. They've got slightly different patterns. For the continental crust, you've got this V-shaped structure on the side, which are quite interesting on the proximal margin, and they seem to be controlled by the interaction of our first order structure and the second order segmentation. The mantle lithosphere, on the other hand, seems to be much more partitioned along the first order structure that we saw. We can look at the evolution through time of this structure orientation. And what you've got here is an evolution. So this plot, you can read that's the time in the axis here. And on the ordinate, you've got the orientation of the structure. Extension orthogonal structure will be oriented like along this line. And when they form, we see that we've got structure which have an obliquity of about here 20 degrees, 15 to 20 degrees. And when they form at what was predicted pretty much by what people doing analog model have been presenting. And when they form obliquely, but then after they tend to rotate toward orthogonality, which is quite nice. And what we see is as this happens, the rift tends to widen. Okay, we've got this first generation of grabens that form obliquely, and as opening sort of propagate, they do widen the active rift system. And at some stage, this structure, they're not going to be able to accommodate much of the deformation. You create some, you've got a narrowing of the active rift. So most of the deformation is now happening in the central part of the rift. It happens over like a 2 million year period. And you've got neoform structure, which are still optimally oriented, and also reactivation of extension orthogonal structure and probably neoform also extension orthogonal structure. And at some stage now breakup is propagating from the side of the model and entering the central part of the model, and you've got an accommodation sort of zone which are formed there between your segment of oblique rift that we see in the system. What we find is that the model geometry has a very strong control on the geometry of the structure. Actually, the localization is always happening in our model on the side along this edge here, because we've got free slip and you've got this weak zone. This is strong material which is pristine here again, so it's going always to start here and going to propagate inside the model. And what we find is that if we change the width of the model, it's going to change the final direction of our ridge, pretty much. So if we've got here a square model, which is 1200 by 1200, our 30-degree obliquity imposed, we end up with a rift, sort of a ridge obliquity, which is of about 15 degrees. But if I take a model which is half the width here, because it's only 30-degree obliquity, are going to have almost an inverse direction or non-oblique rift. And we find that we've got something like minus or 2-degree obliquity compared to what we impose there. So the important message here is that anisotropies or heterogeneities in the system here, which are our edges of the system, are going to be very strong control, more than the theoretical elastic half sort of angle, which is predicted by the model. And well, that's just the 3 models altogether. And I just want to come back to that, the oblique rift sequence. So what we proposed in this paper in EPSL is that we start with this diffuse rifting system where we've got this intermediate oblique direction going on in our weak zone. Rift are propagating towards the edge here or from heterogeneities in the model. And when this sort of wide graben form, they tend to form obliquely and then rotate toward orthogonality. So you have to be very careful when interpreting paleo sort of seismology data if you look on some old faults, because they may have rotated massively. And then we've got this narrowing and coalescence of the structure with amalgamation of this second order structure, which are either oblique or orthogonal. And you preserve all this early structure on the passive margin there, and you open your rift like that. So that's it for the oblique rifting. I'm just going to take like 5 minutes. Do I still have time? Yeah, okay. So in the next 5 minutes, I probably wanted to say too much, I'm sorry. And I'm going to go quickly through the third item of the presentation, which is trying to understand the dynamic of geological structure in reef system and how they impact the surface processes in this system, right? So there are 2 papers that we published a few years back in 2019 and I think 2018 for the first one. The first one is we were trying to understand the impact of fault geometry at depths. Okay, your normal faults. I mean, some people argue that shallow normal faults exist in rifts. Some people argue that you should have a 60-degree normal fault, and we wanted to assess that in a context of the current rift, where various schools or various research groups have been proposing different interpretation based on the seismicity, which is recorded today in a Western current rift. And our conclusion is very obvious, is that high angle, not low angle normal faults tend to dominate early extension in this system. I'm going to show you that in a minute. And then that brings us to more recent work that we've done with Sofia here, Peshlivanidou in Bergen, and the group in Bergen here, where we looked at the importance of this sort of fault uplift subsidence in controlling surface processes and infill of sediment inside the depression. So I take you, when we're not in Africa anymore, we're now in Greece. This is the Gulf of Corinth. South will be in this direction. You've got the Peloponnese here. The Gulf of Corinth is here. It's pretty much running east-west. And in this model, we started with 2-day topography, and we tried to model the last, let's say, 30,000 to 130,000 years of evolution. So we assumed that 2-day topography was as good as it gets as a starting point for the paleo elevation for the surface process. In the first couple slides I show you after, I'm going to focus on the tectonic model. What we did is we actually did only 2D models using another open source code called Pilot, where we try to impose different fault geometry. And we were looking at both the sort of instantaneous response, the co-seismic response, and the relaxed post-seismic response into this system. So I'm going to show you that. And after I will finish with a sort of erosion deposition pattern and what we found in terms of its evolution in the current rift, and see how it's a bit counterintuitive. We expected to see that with footwall uplift increasing in the south of current, we will have massive sediment coming into the system. But actually our models show, and when we compare them to natural data, it seems to be robust, that most of the material is coming from the north when you create this system. So your footwall contribution to sediment budget in a reef system seems to be quite important. So let's dive into current. Current is a beautiful hemigraben, pretty much. You've got a map view here with current and some of the main active normal faults which are presented, and most of the faults, at least to the south, tend to dip toward the north and limit the basin, the Gulf itself of current. You've got here a schematic diagram for this part of the system here, where we try to represent all the possible interpretation for the orientation of the structure. So some people, Sorel, for example, or have been proposing that you've got a very shallow low-angle normal fault that is running through all current. Some other authors, like Rigaud and others, have been proposing that you've got a shallow angle normal fault, which is at from 3 or 7 kilometer depths. So we wanted to test if we could reproduce the behavior in terms of surface uplift and subsidence in this reef system when in a numerical model. And to do that, we used, as I told you, Pilot, and we developed this very simplistic 2D model with an elastic upper crust on which we impose an initial fault, and we're going to play with the geometry of this fault, having it straight, having it like kinked at a certain depth, and we've got a viscoelastic lower crust, and the model is very long, is 1,000 kilometers long, but we only look at the central part along the fault. And this is what the result looked like. The way it's presented, you've got the co-seismic response on the first sort of snapshot here, and the relaxed, the final response here. And the fault geometry is shown in black. Here we've got a fault that runs at 45 degrees from the surface to 7 kilometer depths, and after between 7 and 10 kilometer depths goes to 15 degrees. What we show is that the uplift subsidence, so the co-seismic is in black, create barely any uplift of the footwall when you've got this type of geometry. Most of the system is actually, most of the uplift is happening on the hanging wall of the system here. Like if you had a ramp and you create a kind of an anticline, which is formed at the end. So it didn't really reproduce some of the features that we see. We try with an even shallower sort of low hanging normal fault, and it was even worse. Even after relaxation, after the viscous response shows that everything should be sinking. So we cannot explain the 1,200 meter high elevation on the south of current. We found that in this model, when we've got normal faults, which are running through the whole sort of plastic upper crust at 45 to 60 degree, we create uplift subsidence ratio. So taking the 0 as a reference point of 1 to 3 or 1 to 2, which is about what the geologists looking at seismic interpretation in this system have been proposing. So we argue that in a current rift, shallow angle normal fault are really not controlling the system there. And we wanted to see, okay, now you see this footwall uplift and this sort of block rotation, and same in the hanging wall where you have some progressive sort of subsidence, how it did influence erosion rate. We took this time sort of a simplified elastic half-space model using a code called Coulomb. What you do is you define your fault geometry. Coulomb 3 is a free MATLAB tool that you can download from the USGS webpage. And you define your fault and you impose an amount of slip on this fault, and it's going to calculate the displacement at the surface. So when it's in green here, it's going up. When it's in red, it's going down. And we took today fault trace and we tried to apply that into the Gulf of Current sort of topography. And what we see is that here, so what, yeah, we used another code, which is also open source that you can download. It's called Badlands. It's designed to do surface process modeling. And we run 2 models in Badlands using the same initial topography, one with tectonics and one without tectonics. Same precipitation, same everything else. And we did compare the 2, okay? And this is what you see on this image here, on the top image. So there's you've got a difference in erosion rate. So when we take the model with tectonic minus the one without tectonic, we see that erosion rate is larger in the footwall in the model which has tectonic in it. In fact, what is happening in the tectonic is that you've got subsidence of your shoreline here that we can see in blue. It's not very obvious in this model. So it means that you increase the slope. So if you increase the slope, your sediment are going to you're going to drain larger and larger system and feed the basin in there. while in the footwall of these normal faults, which are relatively steep in here, you're going to have less and less contribution, actually. You're going to feed the basin with a lot of material here. You see the erosion rate is rising very close to the shoreline. But after, when you're inland, because of your back tilt of your system, the faults are going to contribute less and less to the sediment budget. And these are map view with the tectonic. Without the tectonic, you see, so the redder it is, the more material is provided. And this is the difference between the two. So what we argued here is that, well, normal faulting is actually stopping sediments to go into the rift compared to what we tend to believe maybe more logically. And I think that's it. That's my final slide. I just want to give make some advertisement on using numerical modeling for teaching. This is a great tool. We've been using it a lot here in Nice with our students. And a few years back, Romain Beuchet, Louis Moresi, and others, and had a very small input into this work. So all the credits to them. Put together a paper in a journal of open source software. And you can download it in a very simplistic way, run it on your computer I forgot the name, sorry, I should have wrote it down. And anyway, it runs in an IPython notebook, and you can run very simple model. And here, this is an example of salt tectonics where you've got a basin, and we look at the salt migrating into the system. There is sedimentation in the model, very simple as well, where you can look at the age of the sediment. You can look at the fault migration, the different behavior when you're above the salt, below the salt. Students very engaged massively with these tools, and you can run it on a simple computer. You don't need HPC for that. That's it. I stop on that. Thank you very much, and I'm open for any questions.
Well, thank you very much for this very rich presentation of all the varieties of code you can use to do geodynamic modeling, and bringing us very good insight into the dynamics of this system. So thank you very much.
My pleasure. Probably wanted to say a bit too much.
That's all right. That's all right. Is there any question? You can post on the chat, or go ahead, Karim.
So thanks, Guillaume. That was really nice.
My pleasure.
Well, I have few questions. I mean, for the second part, I mean,
the oblique lifting
localization might, I think that magmatism can influence so strongly your. Can you account for this in your?
You are absolutely right, and that's why I said, like, in my simple view of the world, there is no volcanism. Definitely, we see that when you've got full breakup in our system, we see that the mantle, the asthenospheric mantle rising along the ridge is controlling all the localization pretty much. You weaken your system if you've got melt, and people have been showing that before. I think Cynthia Ebinger and so on have been showing that for East Ethiopian Rift, and some modeling work has also been done by Duclaux, where he did some tests with having melts in a model, and it does play a dramatic role. You're right. In the model, in Petatin code, in the way it is set at this stage, we are not able to, I wasn't able at least, to put an equivalent sort of male behavior. When you, the difficulty when you do this, this type of modeling, it's continuous mechanics pretty much. And when you start to have a fluid, because melt is a fluid, that come into the system, the solvers can be a bit tricky to set, and it's two different physics mixing together. So I don't have the experience with putting melt in this type of models, but they will definitely have a massive importance. You're right.
And I understand that also for the evolution of your faults during your oblique extension, you've been testing how sensitive it is for geometrical changes, but how sensitive it is to changing in rheologies.
Yeah. Oh, well, so this is a paper I need to finish writing. You're absolutely right. Or either changing the rheology or changing the temperature, for example, of the model. That's going to have an influence on the rheology. And we did play with that. If the model is weaker, let's say your crust is not as stiff as it is in this model, you will tend to have a much broader or wider rift system. And the deformation is more distributed, and so on. Yeah, so the rheology definitely have an impact. And again, either you play with the rheology or you can play with the temperature. And it goes toward your first point. If you in a system where you know magmas are present, definitely the system is going to be hotter. So it's going to have a weaker rheology. So it's all sort of working together, I suppose, in a sort of loop.
Thanks. And the third question, and then I stop, is regards your Gulf of Current thing, normal faults. I mean, my experience with the Italian normal faults is that at least what we see, I mean, chasing all the earthquakes that took place recently, is that we're observing a long-lasting afterslip that are going on, and with high-resolution seismicity relocation, we're observing long-lasting afterslip that are going on the decalments that are right beneath the high-angle steep normal faults. This is just an information that might be of interest to you.
So I've been, so there's some colleague working on currents here in Nice as well. And what we discussed actually, what people do, and we didn't either, take that into account, but there are a series of naps which are actually formed when you form the illinites. And you've got this sort of, sorry, difficulty to see, east dipping sort of naps, which are underneath the Gulf of Currents, and with shales which are present there. So chances are you may have a lot of fluid being released in there, and seismicity being localized on this sort of heterogeneity in the system. But census Duclaux are not false, there are more heterogeneities in the system, if I...
Right.
Yeah.
I mean, is there any thinking on your, because my understanding is that you're doing simulations at least for the last 10,000 years or so, then maybe the use of, well, I'm not a geologist, but the use of sediments is quite interesting, but maybe at that time scale, the use of drainage may tell you more.
Well, I did talk about the sediments only, but there's some really fascinating features as well in current, where you've got some of the lakes there, some of the drainage basin there, used to drain toward current, and now they drain, they internally drain, so they're not connected anymore. There's a Stimphalia Lake, which is famous in Hercules 12. I don't know how to say it in English, les travaux d'Hercule. His workouts, sort of, where he had to kill all the birds, you know, in Stimphalia, because they were present there. And Stimphalia is just there, actually. This is this white system here. So there is a basin that used to drain toward current, and that now has been totally captured because of the footwall uplift and this back tilt. And the erosion didn't manage to keep up with the uplift, and you decrease the amount of sediment that can come inside the system. So you definitely modify the drainage. You're absolutely right. And there's some colleagues, David Bianco-Ferrer and others at IPGP in Paris, who did some work looking at this sort of drainage evolution through current, and looking at nick point propagation and these kind of things as well.
Thank you very much. It was nice. Thanks.
Thanks for your question.
Any other question? Okay, so I'll have one which is connected to what was just discussed. Do you have information about gravity currents in valleys at the shore of at the edges of your Gulf of Current on both sides?
You mean turbidites?
Yeah, turbidity currents.
I don't. I know there was an IODP campaign 3 years ago or something like that, where they looked at that. I'm not the right person to answer that, I suppose, but this data exists. Okay. Definitely, and there are actually a bunch of papers by Lisa McNeil I'm probably not citing the first author, but and Rob Gothorpe and so on, that have been published in the past, let's say 2 or 3 years, following this IODP campaign, where they tried to, so they did some coring inside the Gulf. Somewhere here in the middle, they did a few cores. I'm not exactly sure where. Yeah. And I'm not sure about their conclusion, but yes, data exists, and definitely there are gravity currents going on there, because what you build in the Gulf, they're very much alluvial fan, right?
Yeah, exactly.
And from this alluvial fan, the code is not of it. This version of the code is used of Badlands didn't have really the capability to capture that and create canyons and this kind of stuff. Okay. In the latest release, this has been added, and it will be very interesting to revisit this model and see if we produce this kind of hyperpycnal flows that you could imagine happening at the top there.
Yeah, because it's a very good also way to find out about the transport of sediments.
Absolutely, absolutely. Yeah. And I mean, I didn't really get into that, but this is really one of the powerful things with Badland, with this surface process code developed by Tristan Salle in Sydney University. As you can look at the stratigraphy, you take your model, you've got the age of the sediment, you can look at where they deposited, at which depth, and this kind of thing. So you can play with sea level variation. You can even impose some flexure in the model, depending on where the sediments are deposited. So the thing is, in the version I'm using, it's not fully coupled. I can do a one-way coupling, kind of calculate the surface uplift in a code like Underworlds or Pétatin, and use that as a displacement field for my model. But I know Tristan is working very closely with Louis and other people in Australia, and they want to build a two-way coupling between their code. I don't know how far they are yet with that, but this is the holy grail. There's some other people working on that in GFZ, like Jean Braun's group is also very active in this topic. Yeah, no, I was not aware of this code actually. Yeah, Badlang is awesome. It's really good.
Yes. Okay, so I think I don't see anyone popping a question, so I think we'll end there. And again, thank you very, very much, Guillaume, for your presentation. It was really good.
I thank to you all for listening, and thank you for the invitation once again, Catherine. It was a pleasure. Thanks for the question. Yeah.
Merci, Guillaume.
Pas de quoi.
Allez hop. Ciao, merci beaucoup.
Ciao.
Have a lovely day, everyone.